1, 2, 3, 4, 5. This has been a successful conclusion of our audio synchronization test for today. Thank you very much. We will begin the lecture at 11:30, as usual. Gets me every time. Thank you. So, anyway, that thing that I was just saying, well, first of all, I said, why don't we start on time? And that it seems the universe conspires against me. Oh my goodness. What was I saying? Oh yes, so JHub. So, with respect to the assignment system in JHub, things are now to the point of you should be able to fetch and submit the test assignment. That's been distributed now. It's not a real assignment, it's just a systems test to make sure that the system is working. It would be a good thing if you logged in, all of you logged in, tried to get that test assignment, just make sure that the system works, and if it doesn't work, then, follow the troubleshooting procedure listed in the course syllabus, or email myself or one of the TAs about your problem, and we can get these problems sorted out before it cuts into the time that you have to the time that you have to perform the assignment material. So, yeah, that's insofar as JHub is concerned. Aside from that, let us continue with our lecture as it was occurring previously. Yeah. So, last time we were talking about how one goes about doing some basic I/O stuff. We're not getting into files and file streams just yet. Right now, we will contain ourselves to dealing with standard input and standard output. Quick review of those. Standard input is a buffer internal to your computer which logs your keystrokes. This buffer is read from by programs in order to acquire those keystrokes and do things based on the keystrokes. Standard output is your standard outputs. Oop, that's a lot of Python. There. Standard output is a output stream that allows you to see stuff going on. It writes stuff back into a terminal that you're using. So, for example, let's see, I think I probably have something that prints something. Yeah. So, this hello world, those characters were dumped into stdout, and the bash environment picks up stdout and prints that as characters on the screen, using arcane and abstract mechanisms. So far we've talked about how to put stuff into standard output. We have not yet talked about how to acquire things from standard input. So this is the procedure. The following program uses the scanf standard library function to read keystrokes from the standard input buffer. We have a program to add two numbers with user prompts. We're including stdio.h as usual. Int main void, int I1, int I2, printf, enter your first integer. Then scanf, scanf is the new one. We've got this weird thing going on, and then this weird thing going on. We're going to talk about both of those things. We perform that procedure twice, and then we print the sum. So, let me just see if we've got that. I should have that somewhere. Yeah, probably add.c. Yep, that's add.c. I'm just gonna, and that's already compiled to an executable. So add, there we go, enter your first integer, 10, enter your second integer, 89, the sum is 99. There you go, relatively straightforward. Checking. Question. Sorry, but would it be okay to briefly re-explain what include... yeah, the include statement. So include is what's called a preprocessor directive. In the case of an include statement, the function is to go out into your computer system and find a file that contains code that you're going to use in this program that you don't want to define in this program. stdio, we're talking about definitions for functions. stdio.h contains the function prototypes for printf and scanf, which, if we didn't include stdio.h, we would not have printf and scanf available to the computer system. So, for example, if I were to, well, maybe you can just take my word for it. It would tell me that these functions were undefined. So, it's correct to say that the analogy is to import in Python. It's, as with most things going from Python to C, it's like a slightly different thing, but the overall gist of the thing is pretty much the same. Hopefully that answers your question. Yeah. stdio is standard input-output. Okay, so, and, just for the purposes of the slides, this is what the output looks like when you execute the program, which, I just showed you live, so there you go. So this program has a lot of stuff going on in it, so we're going to talk about the things that are going on in it sort of in the order that they appear. So, first of all, you might notice that this program uses variables, I1 and I2 in particular. Variables in C work the same as in other C-based languages. So a variable in C and a variable in Python, at a high level, they work in almost precisely the same manner. The only differences are Python does a little more bookkeeping behind the scenes. Like, for example, in Python, you don't really have to worry about limits on the size of an integer, right? Like, in an integer, oh my goodness, it's 16 bits, I think, in C. Refer to the chart in topic 1. In Python, once a variable is declared as an integer, if while using that integer you exceed the size of that integer, Python will just allocate more and more memory in order to store the larger and larger number. You, as the user, all of that detail is hidden from you and you don't have to worry about it. In C, if you try to add 1 to an integer that is larger than... if you perform an operation on an integer which causes it to be larger than the size of an integer in memory can accommodate, you get a thing called wraparound, which we'll I don't think I have an example of it in the slides, but we'll get into it when we talk about bitwise and bit representations. But essentially, what happens is it does not expand the amount of memory that's holding the integer. If you have like the maximum number that can occur in an integer and you add 1 to it, you get 0. If it's an unsigned integer. If it's a signed integer, I believe it flips to the largest negative number, or the smallest the most negative number it's capable of representing. So, in contrast to Python, variables in C require explicit declaration. So, in Python, a variable is declared implicitly on its first use. So, you would write some assignment statement that would, use X for the first time, and X would suddenly be a thing, and you don't have to worry about specifically declaring what data type you want that variable to be. Python infers what the data type should be from the thing that you assign to it, Python's relatively loose with its dynamic typing anyway, so to some degree, it doesn't super matter because it's got all this bookkeeping in the background that takes care of it. In C, you must explicitly declare variables. When you declare them, you must declare them with their data type. The data type tells C, it tells the program how much memory to allocate to a particular variable. So, if it's an integer, you get so much data. If it's a float, you get so much data. If it's an array, you get, whatever the base type of the array is multiplied by the size of the array. That much memory is set aside, specifically allocated to that variable. So, C cannot use a variable doesn't exist unless it also has that piece of memory set aside for it. The syntax for declaring variables is that you use your data type tag. I don't know. You declare the data type in front, and then you can have a comma delimited list of whatever your variable names are, or you can just have a single one. And as always, everything gets terminated with a semicolon. When you're declaring variables, you may also give them an initial value. And if we want the initial value of x to be 7, we can put the assignment statement right in there in the declaration. This is sort of most similar to the Python syntax. Python just leaves this bit out. So if you do not choose to initialize a variable, I'm pretty sure this is universally applicable, but I know it's applicable to pointers. C does not overwrite the data that's existing inside of the memory that's been allocated to a variable unless it's specifically told to do so. So, basically, what the end effect of that is that when you, for example, declare a float, and you don't initialize that float, that piece of memory will just contain random ones and zeros that are the results of previous calculations and previous uses of memory on your system. So, in some sense, it's a random number. In order for it to be useful data, you have to actually initialize the value. So, the take-home message is you should probably almost always initialize a variable, even if you don't need an initial value, to something like 0. Or, whatever you want the initialization to be. This process is known as instantiation. So declaring memory is different from instantiating memory. You can the process of allocating the memory, that's declaration. The process of telling that memory what its initial value is, that's instantiation. Let me see if I have any questions. Yeah, so this is a issue that we were having earlier in the week. If on your JHub assignments tab, everything is just loading and loading infinitely, the thing that fixes that, as your compatriot has declared in the chat, is that if you go to the control panel, which is in the top right-hand corner of the screen, and go to and shut down your server and then restart it, that should fix the problem. So that's also a good way to kill any processes that might be running on your server that might be causing you problems. So there you go. Cool. So the identifier naming conventions. There are particular names which are legal for identifiers. Variable names are a type of identifier. Function names are also identifiers. Identifiers are legal if they contain only letters, digits, and underscores, and do not start with a digit. Letters can be upper or lower case. Identifiers are case sensitive. So here are some good practices. Starting identifiers with underscores may cause conflicts with identifiers generated by the compiler or with the standard libraries. Generally speaking, you should avoid starting any identifiers with underscores. It might cause conflicts. The purpose of the reason that a lot of these libraries start their identifiers with underscores is to try to prevent them from interfering with your identifiers. So, don't just stick to your own territory with respect to that naming convention, please. Like many things in C, starting identifiers with underscore is possible, but not recommended. You should always use meaningful variable and function names, unlike on the preceding slide where everything's x, y, and z, or foo and bar are also common placeholders for slides. By convention, variables and functions begin with lowercase letters. Again, this is by convention. Multi-word variable names can be separated by underscores or written in camel case, and those are of course only two ways of doing it, but those are pretty... Again, this is conventions rather than strict requirements. So, let's get to scanf and the standard input buffer. The standard library function scanf reads characters from the standard input buffer, stdin. We've got two arguments here. The first argument is the format control string, which indicates the data type that should be input by the user. %d is an integer, like a regular integer. So there are a bunch of these format control tags, which we will be dealing with when we are talking about types in just a couple of slides, actually. It's kind of... The reasons that it has to be input like this are arcane, so at this point in time I'm going to ask you to just memorize that this is the way in which scanf is to be used. If you're curious about the reasons for it, you're absolutely welcome to do some noodling around on the internet to find it, but, yeah, anyway. The second argument here is the variable that we want to put the data into. This ampersand is the address of operator. So scanf actually takes a format control string and a pointer. This ampersand turns any variable into a pointer. Essentially what it does is it returns to the program what the specific memory address of the variable it's been given is. That's why it's called the address of operator. This is not really something that you have to worry too much about right now. We're going to be talking about the address of operator and how to deal with and work with pointers in a few weeks' time, before the midterm recess, I think. And let's just say it's its own set of slides, and we'll be going through it in nauseating detail, so don't worry too much about it right now, essentially. But yeah. Questions? No questions. Okay. Unless this isn't updating. Let me see. Pop out. That usually refreshes it. Doop-a-doop. Nope. Okay. Good. How are numbers? Yeah, that's not too bad. So, there's also a... we're using printf in a manner that hasn't been seen before as well. We're using printf in a manner that allows us to display the values of variables and send them to standard output. So, in order to place the data that you want to print inside of the string that's being sent to standard output, you have to insert this format specifying placeholder tag in the position in the string where you want the data to be stuck. In this particular case, the data that we are sticking in there is the result of I1 plus I2. So in order for this to work, there has to be a format specifying placeholder inside of the first argument, which is the string, and the thing that you want to write should be the second argument to printf. So there you go. Each data type has its own placeholder. Here is a list of the fundamental data types available to you in C, their size in bytes, and which placeholder you use in order to access that particular data type. So you'll notice that a lot of these ones are int with a couple of other tags applied to it. So this is the way that C chooses to deal with the fact that, you could, in theory, want a few options on your integers. Appending the short tag to an integer reduces the size of the integer, so it chops it in half from 4 bytes to 2 bytes. Making an integer unsigned means that that integer becomes incapable of representing negative numbers. It can only do positive numbers. But because of that, the number of numbers that the integer can represent stays the same. So you can represent the magnitude of the numbers that you can represent is multiplied by a factor of 2 if it's an unsigned integer. But if it's a regular integer, I believe it uses 2's complement. Again, we're going to talk about this in a bit more depth when we talk about bits and bitwise and bit representations. If you wish to make your integer long, then you can make it, if you append or prepend the word long, you double the size of it. Long int should be bigger than 8, I think. There might be an error in these slides. I'll check that and submit I'll update the version. If that's true, it's also incorrect in the textbook. So, you will have a couple of other sort of miscellaneous data types aside from integers as well. We have char, or character. The strings are composed of characters. Note that the standard character size in C is 1 byte, so that's 8 bits. That means that in a C program, ASCII characters are or extended ASCII, the one that uses 8 bits, that is the character set that you have to work with by default. If you want to use UTF-18 or some other character set, you are going to have to do stuff in order to make that work. However, for the purposes of programs that you would write in C, normally this is enough space. 1 byte is all you need. We also have floats and doubles. A float being 4 bytes, a double being 8 bytes, and a long double being 16 bytes. And if you wish to use these guys in strings, here is some handy reference for the placeholder tags that you would put in the strings. Cool. I'm going to check to see if we have any questions. Questions! Okay. Would it be possible to insert multiple integers into a placeholder? You would use multiple placeholders. So let me do that for you in code. So get it simple.c. There we go. So there and there. And let's say I would like to do I and j. I believe it's in separate arguments that you do that. GCC simple.c simple. There we go. No compiler errors. Run simple. There you go. That's how you do it. That's how you do multiple. So, more accurately speaking, this would be you would have as arguments, separate arguments, all of the things that you wanted to write, and there should be one placeholder for each argument after the first. Hopefully that answers your question. How to determine the size of an integer? It's in this chart, right there. The size of an integer is 4 bytes. No more, no less. So, you may have noticed that the foregoing slide didn't have booleans on it. Those of you who are used to programming in languages other than C may be used to the idea that a boolean data type is a thing that exists and you can declare boolean variables. The awful sad truth is that support for booleans was added to C in the year 1999, which is not that long ago. Although, I think we're kind of getting to the point where this might be, booleans in C might be older than some of you guys are. But needless to say, for a language that was invented in the 70s, the fact that it took until 1999 for them to have support for booleans is quite an interesting thing. That should indicate to you the idea that stability is the design ethic of C. Stability. So, anyway, unlike most other languages, booleans are not part of the C prelude. What I mean when I say prelude is that you don't have to import a library to determine what an integer is. That's loaded by default. C knows that by default. It's in the prelude. In order to use booleans, you have to include the standard boolean library. So if you include stdbool.h, that means that you can now use booleans in your C program. Prior to the existence of a dedicated Boolean data type, C programmers would use integers to represent Boolean values. 0 meant false, and anything that wasn't a 0 meant true. Typically, 1 is used. And interestingly enough, that is actually how the underlying bit representation of Booleans works as well. One would think, since a Boolean is a binary piece of data, it's either true or false, that in the underlying implementation in hardware, that you would only use 1 bit because you only need 1 bit. But, as it turns out, that's not actually the case. Booleans are used, when you declare a Boolean variable, the container that it's given is at least a byte. I don't know, they might be doing short ints, but yeah, they don't just give you 1 bit for a Boolean. And part of the reason for that is the manner in which memory is addressed in a computer. So, this is kind of a advanced topic that we're gonna talk about this kind of stuff when we get into how the memory subsystems of your computer work. You know, because this is a course in C, but it's insofar as we become good C programmers, it is necessary to know a certain amount of computer architecture. So we're going to be talking about computer architecture in this class as well. So the way that memory works, very roughly speaking, is you have this vast grid of memory cells. And in order to access some group of memory cells within the memory chip, that requires a memory address. So it gets complicated because it's like electronic circuits and multiplexers and all kinds of things. But essentially, there's a circuit that if you feed it in an address, it will return back out through its output port the value of the memory cells at that address. So the question then becomes, how many memory cells are represented by one memory address? And it turns out that it's a byte. That's why bytes are so important in computing. A byte, like each byte in your memory, has its own memory address. But that means that you can't address bits individually. There's no way of accessing, well, you could do it, but you'd have to write more commands to be able to, like, perform a mask operation over the bits to be able to extract one bit out from a set of bits. It turns out that memory is not so expensive that you can't dedicate, an entire byte or even several bytes to the existence of a Boolean variable. But yeah, you can't offer you can't expect the memory chips to be able to pick out individual bits out of your system's memory. Those have to occur in clumps of 8. So that's why that happens that way. I'm going to look to see if there are any questions. Questions! Mostly born in 2001, eh? Yep. What does the error undefined reference to win main 16 main? I don't know. I don't know. So can we not declare a statement without a declaration? Yeah, or you can't write a... Yeah, so... If you try to use a variable that has not been declared, let's say Q, what'll happen is that you will get this error, and this is a hard error. Q undeclared, first use in this function. There you go. So if you try to use memory that if you're trying to use okay, so this is how things are working underneath the surface, right? The program generates this like during the program compilation, all of these variables, like the computer program that executes doesn't care what you call the variables. These variable names are eventually, in the compilation process, replaced with the memory addresses of the things that they represent, right? So, in a sense, the variable names themselves only are applicable to you, the programmer. The machine doesn't care if it's named I, J, or Q, or whatever. So, because of that, during compilation, there is essentially a lookup table that is built that maps variable names to memory addresses. What happens when you try to use a variable name that hasn't been declared yet is the compiler looks up in its lookup table, it looks up in its table mapping variable names to memory addresses, notes that the variable name it's looking for it does not exist in the table, and says, that is an error. I will terminate the execution of this compilation process in order that you might fix your dang code. So, hopefully that's an answer to your question. So, variables. Here are some, I think I've already kind of covered some of this, but let's talk about it anyway. Variables are units of memory that have been assigned to an identifier. The amount of memory allocated is dependent on the data type the variable is declared with. The specific arrangements of ones and zeros at the memory location the variable indicates, that's the value of the variable. Unlike in algebraic variables, a computational variable always has some concrete value, even if it's junk data, even if you think you've declared it as null in like Python or whatever. It's not like setting a variable to null in Python causes a little black hole to open up inside of your memory chip so that there is no matter there. It's not like calling something void turns it into like the absence of an electronic circuit. And it's an electronic circuit, so it has to be a 1 or a 0. It's not like some intermediate value either. So what happens in those cases is there is some specific underlying representation that the computer puts there. It just interprets that particular arrangement of 1s and 0s as a null type in Python or whatever. A variable may be read from without disturbing the underlying memory. And when a new value is assigned to a variable, the underlying memory is overwritten with the new value. So that is to say that reading variable values is a non-destructive process, and writing variable values is a destructive process. Of course, this should be intuitively clear to anybody who has spent enough time in the same room as a computer before. I'm going to check for questions. Cool. So, in Python, variables don't need to be declared with a data type. That's because Python will infer what the data type should be from the things that are being assigned to the variable. This is known as dynamic typing. The Python interpreter manages the memory representations of the variables, as I noted with it expanding the size of an integer to accommodate the size of the data that that you, the user, wish to represent. The user, you, are protected from these and other low-level details. This is why people consider Python to be a high-level language, because it's doing a heck of a lot of work behind the scenes to make sure that you never have to worry about the memory representation of a variable. In C, the type declaration tells the memory system how much memory to reserve for the variable, so the information must be present. C is not going to hold your hand. It's not going to make assumptions about what you meant. This is one of the biggest differences between C and Python. Python will absolutely, it's like, well, I think you mean this, so I'll just do it that way, and if that's wrong, I'll change it. Whereas in C, it's like, you need to tell me what you want. It's like going to a restaurant. It's like going to a fancy restaurant where you can say something like, just get me whatever's good. And going to a McDonald's where it's like you have to enter your order very specifically or you won't get what you want. Anyway, variables in the same program will not necessarily be allocated adjacent memory cells. That's a very interesting thing as well. We'll get into this a lot more when we start talking about pointers and memory addresses and that sort of thing. But you should not assume that any variable you declare is going to be right next to any other variable that you declare. This will actually be a thing that you have to worry about when we're talking about pointers. So, essentially how the memory gets allocated is when your C program starts up, it is allocated a certain amount of the memory to play with by default. Then that program will assign variables inside of its little playground of memory. And, if it goes outside of its playpen, the operating system will hit it with a big hammer and say, no, that's a seg fault. But inside of the program's playpen, the order in, the positions, the actual physical positions of the variables that are being declared is not something that's predictable by the programmer. So you have to be able to work on the assumption that the variables that you're declaring can be anywhere inside of the memory space that's been assigned to your program. Questions? Since an int is 4 bytes, does it always take 4 addresses in memory? Yes! That is precisely what that means! Thank you very much! Good! Yes, you're getting it! Awesome! Yes! Good job! Good, good, good. So that's all we need to know about variables and some memory concepts for now. So let's talk about operator. Get me Chicago. We'll talk about operators. So there are a few new operators here that you probably haven't seen before. So don't. We're going to talk about these guys, but these guys are real easy and useful. So these are your arithmetic operators. We've got x plus plus, x minus minus, plus plus x, minus minus x. Those are different things that are interpreted in different ways. That's why they have different lines in this table. You've got negation. You've got addition, subtraction, multiplication, division, and modulus. Arithmetic division occurring on integers is integer division in the Python sense, so that's equivalent to your double slash division. Here, I can prove that to you too. Let's go back to simple.c. Let's make this a division operation, just so. And let's say, let's just get what z is. There we go. Compile that up, execute, and there you go. So it thinks that the value is 2. Notice that we're interpreting that as a integer as well. So in Python, this would return a float. Our tag for floats is f. So let's replace that with an f and see what we get. Aha! Well, actually, so let's declare that as a float as well, so that it doesn't complain. Note that, although this is a float, the division that has occurred, we've lost the decimal places, essentially. So you got to be careful when you're doing this sort of thing. The way in which you would perform floating point division, I believe, is if you make everything involved a float. But let's just test this. Yeah, there you go. So the division operation that is performed is dependent on the it's dependent on the types of the things that you put into the function or into the operation. So if you are performing division on integers, you will get an integer back, even if you're casting it as a float. And if you are performing floating point, if you're performing the division using floating point numbers, you will get a float out of it. Hopefully that's reasonably straightforward. And of course, modulus operates in the manner you would expect it to. Let's see questions. When declaring arrays, how much initial memory is allocated to it? Would then the memory allocated to it change whenever the values are added to the array? So the interesting thing about arrays in C is that arrays are static. If you are declaring, well, there are two ways to work with it. You can work with static arrays or you can work with dynamic arrays. With a static array, the size of the array is declared up front, so it's all you're doing is, you know, like the system will set aside a continuous lump of memory that's the size of the array, and that's its array, right? And that's it. You can also, once we get into pointers, you'll see this. You can also say, I am going to declare a pointer, which I'm going to interpret as an array, and then there's a C function for allocating memory to that array, and then you can allocate and deallocate memory using functions in C. So if you wish your array to be able to grow or shrink dynamically depending on how many things you put in it, you actually have to do the groundwork yourself for that using memory allocation functions. Don't worry about that yet. We're going to get to that when we talk about pointers. There's going to be like many slides on malloc. How does memory allocation work with string variables? Strings in C are static, so the description that I just gave for how static arrays work applies to strings. Just the element of the underlying elements in strings are, of course, characters. Can only one be a float? That's a good question. Let's see what happens if we make this one an int. There we go. We still get a float. So it seems if one of the two inputs is a float, then you get a float back out. There you go. Question. So does casting it as a float work with I and j both being integers? Let's take a look. I think you would have to cast them as integers prior. Oh, there you go. That does actually work. Wait, did I save this? Oh, that works. Okay, so casting float like that works. Incidentally, for those of you who are not sure or have never seen this before, I'm sorry we haven't talked about this, but this is what's called a typecast. This converts the thing that it's in front of to the data type specified. So if I were to do that, and then there we go. That, that casts it as an int, even if these are floats. There you go. Incidentally, floating point to integer translation is a truncation operation, not a rounding operation. So the decimal, however much the decimal, the fractional component is worth, it will be dropped entirely. So you can think of it as rounding down in all cases. Yeah. Is there a way to do float division with integers? Yes, cast it as a float, as we just saw. There you go. So there you go. That's all that question. That's all that stuff. All right. So let's talk about increment and decrement operations. I should be able to get this next two slides done, I think. The increment and decrement operators, plus plus and minus minus, respectively, will either add or subtract one from the operand. Both of these operations use implicit assignment, so no assignment operator is required. So doing something, for example, like I plus plus, that is a statement in and of itself. You can just put that in a line, and that is syntactically correct. Whether the operator is prefix or postfix affects the semantics. So if you put this operator before the variable, i.e. that's prefix, the increment or decrement operation is executed before the containing expression. If the operator is postfix, i.e. it's been put after the variable, the increment or decrement operation is executed after the containing expression. Obviously with this, it doesn't matter because the only operation being performed is the increment operation. However, it's possible to use plus plus inside of other expressions. Because of this implicit assignment, using the plus plus or minus minus operators on an integer literal is a syntax error. You can't increment literals because you can't assign to literals. It doesn't make any sense. Yeah, so essentially, I've got a good example here. This is the increment example. We've got two variables, both var1 and var2, which are both initialized to 5. We've got printf, variable 1 is equal to var1 plus plus, and variable 2 is equal to plus plus var2. You will notice that this is the postfix operation, which means that this incrementing will occur after the containing expression or statement has been executed, which means that at the time the printf is executed, the variable's value is 5. Whereas, if you prefix the increment operation, the increment is performed before the containing expression. You can think of it as inserting itself above. So, when the printf statement gets executed, the var2 will already have been incremented, so the printed value will be 6 rather than 5. I think that is that's time for today. I'm just gonna. It looks like we don't have any more questions, so we'll just end the stream there for today. Thank you very much for your time and attention, folks. I'll see you in the next one, I guess. I'll stick around for a couple of minutes if anybody has any questions.